Hi, my name is Joel Viccars from the University of Calgary. I work under Dr. Burlingett, and my project is basically to produce more highly efficient dyes for the dye-sensitized solar cell. My particular project is actually aiming towards trying to reduce recombination from occurring from after we get photoexcitation of our electron into our tin oxide. We want to try to stop it from recombining with our oxidized dye. So by doing this, we came up with an idea. Not only could we try to, by incorporating a second donor over here, we can try to not only be able to build up our molar absorptivity, absorb more light. We also hope to actually be able to transfer our electron from our ATPA unit or triphenylamine unit down to our metal, and then create the hole further away, so we can try to increase the distance, so we can try to reduce recombination. But to do this, we have to be able to tune our redox centers, both located at our TPA unit and our metal center. So by doing this, we can either put electron donating groups or withdrawing groups on our R groups or R prime groups. So essentially, to get this electron cascade or hole transfer, we need to really put more electron density onto our TPA unit. So by putting this methyl oxy group, we can put more electron density on, bring up our HOMO, and then hopefully by putting electron withdrawing groups in this situation, we use trifluoromethyl group to bring down our redox potential on our metal center. And by doing this, like I said, we can get this hole transfer. So by photoexciting our dye, doing a metal to ligand charge transfer, it then gets excited up into our acceptor ligands, which then are actually have these carboxylic ions, which actually bind to our tin oxide, or sorry, our titanium oxide, which helps with efficient hole transfer. And so now, once that is excited up, we can again get our electron to relax back down, and hopefully with the hole moving over, we will prevent this excited photo-injected electron from going back into our oxidized cell. So my goal is that we have already generated, our goal is to try to kind of see, by modifying our spacer unit between our two redox centers, see if we can try to reduce the rate of recombination. So we have three cases here using a thiophene linker, vinyl linker, and like our saturated ethane linker. And we have actually done recombinations and transient absorption spectroscopy on our thiophene linker. From our transient absorption spectroscopy right here, we see that after we excite the electron, we take excite the dye to get electron excitation, we take an absorption spectrum, and this right in here, this blue region, we get absorption around the 740, which is actually signature of absorption spectrum of oxidized triphenylamine group. So we feel that we're getting this whole transfer. So now we're like, okay, we're getting it. Now let's see if we're actually retarding any electron recombination. And we've actually done some studies on it, and it actually shows that by, because we have a few derivatives of this type of dye, ones where we actually do get hole transfer, and ones where we don't get hole transfer. And we've done recombination studies on both of them, and they both show the same type of recombination. Therefore, hole transfer in this case is not inhibiting recombination. So we have developed a vinyl linkage, and we haven't done any studies on that quite yet, but we're also in the progress of doing a saturated linker to see if there's any difference of recombination occurring there. And what we learn from there, we can go to the next step. We need longer linkers, or we're just actually having it saturating, kind of canceling out the conjugation, will actually help with, recombination. But that's the overview, just trying to bring up our efficiencies by trying to stop the electron from recombining with our dye. So just kind of like a generic overview of our synthesis. We start off with simply Novenhagen condensation to form our biphenyl, our phenylbipyridine ligand, and then by doing the Suzuki cross-coupling with our halogen and our boronic ester, we can then form our donor ligand, our bichromic donor ligand. And essentially we do the exact same, similar thing here. We know we get our phenylbipyridine by doing the typical Novenhagen condensation. We just, we reduce it down to alcohol, and then we oxidize it back up to get to our aldehyde. And then by coupling that with a phosphonate group, we can then do a Wittig reaction to get our vinyl linkage. So these two have been done. Right now I'm working on actually trying to make the saturated linker. So essentially it's very similar to what we're doing. We end up getting our phenylbipyridine again, brominate it, put our boronic acid on it, and then try to do another Suzuki cross-coupling to try to get our saturated linker. And then once we have our bichromic donor ligand, we can then just couple it to our metal terpyridine ligand by doing CH activation with ethylmorpholine. And then once we have our dye, we can then sesquantify it to get our carboxylate ions. So then we can then kind of bind with our titanium oxide. So that's pretty much the generic overview. We have done further absorption studies with our vinyl and thiophene linker. As you can see, we're actually getting good molar absorptivity, pretty much all the way up to a 650, and we're actually getting absorption past the visible region and into the near IR. So this is very good because the whole purpose is try to absorb more light in where light's given off more from the sun, which is more in the red and near IR region of the solar spectrum. And so right now that's what we're focusing on, and we're just trying to really get this saturated linker out, do some studies on it, and then from there see what we learn and go to the next step to hopefully make more efficient dyes for the dye-sensitized solar cell.
Now between the valence and conduction bands, you've got a forbidden gap. And if the gap you've got is just too wide, you'll lose your photons in a snap. Now if the gap you've got is far too narrow, you'll catch the whole darn fleet. But that won't do you any good, cause all you'll get is heat. Oh, solar energy, yes, solar energy. We can have our fun with the power from the sun using good old PV.